wrong lights, actually. Okay, thanks. So, good morning. Thank you for coming. Last day, first session, not so easy, right? And special thanks to Wolfgang for amazing introduction, actually, to my presentation. He was speaking about quantum computing and quantum threat, and actually I'm going to speak about other way around, how where somebody sees actually a problem, other guy sees opportunity, and that's actually a chance for us to introduce some protection methods. And actually, we are not introducing protection methods, we are introducing solution how those protection methods that Wolfgang mentioned being very expensive can be actually cheap, fast, and affordable. That's exactly where CryptoCPU is coming into play. It's our custom dedicated hardware solution, chip actually, that Ponos Technology is developing as a solution for acceleration of various cryptographic primitives that are actually core of post-quantum cryptography. So yeah, we've all seen that we are all following the Ethereum evolution and roadmap, and it's actually mostly, there are many assumptions that it will be strongly based on different kinds of zero-knowledge computations and consensus layer. Also, on the other side, it might be possible to move from EVM towards RISC-V. That's another possible trend. And definitely, entire stack has to be post-quantum resistant. That brings us to the fact that all these kind of computations will be quite costly and also increase latency as there's post-quantum cryptography requires actually much more, 2 orders of magnitude, actually more computation resources than regular cryptography. What CryptoCPU actually brings in this landscape? So first of all, it's a RISC-V based platform that is extended in 2 directions. One direction is extension of different, we'll see it later on in greater details, but we actually extend instruction set to support different kind of specific arithmetic field operations. And on the other side, on the other dimension, it extends in a number of coprocessors that are performing parallelization and pipelining of critical functionalities like hashing entities and so on. Essentially, it is focused on enabling fast and affordable post-quantum computation, focused on zero-knowledge proving. We'll see how it is done later on, but also can be used also, for instance, for Solana validation outside Ethereum, and also it's compatible with modern fully homomorphic encryption methods. What's the essential idea of this one is that usually ASICs are considered as some devices that are sitting somewhere in a corner and very difficult to be used because they're difficult to be programmed, require some kind of firmware and so on. That's why actually we rely on, is that working? Okay. That's why we rely on RISC-V architecture, because it's very flexible and it's, yeah, can go here. That's why we rely on a RISC-V architecture, because in that case, you don't need a dedicated compiler. You can use extend and optimize existing compiler, regular compilers, so that programming interface towards developers remains the same, meaning that they can program in any high-level language without caring about any kind of details underlying implementation hardware. That's one level of compatibility. Another level of compatibility lays actually exactly here, because we consider this chip will be packed in a board that will be through PCI interface connected with interact with the rest of the world, which in practical terms means that server or data service operators can just plug in this card directly into their racks without any kind need of further integration, which means that practically an entire stack, it's fully compatible what is out there. And that's a huge advantage of this architecture, of this solution, because of it's based on RISC-V architecture. Practically, it's going to be a multi-core CPU setup. and having few standard RISC-V cores. Few cores that we will see later will be in charge of native execution of native witness generation. That is the first part of zero-knowledge proofs. And then on the other side, through a number of extended vectorized instructions, meaning prime field operations, plus this set of special function units or coprocessors, if you wish, it will be able to support both end-to-end execution of zero knowledge in a very, very accelerated way. I would just like to give you, a lot of people is asking us about why not GPUs and what's the difference, how it differs from GPUs. So I'll just give you a few insights on that. For instance, when it comes to zero knowledge proof protocol is composed of two parts, so-called front-end, or if you wish, witness generation, that is usually based on RISC-V instruction set architecture instructions, and it practically, GPU must completely emulate execution of witness generation. On the other side, we can make a dedicated RISC-V core that will natively execute this part of zero-knowledge protocol. That's one of huge advantages compared to GPU when it comes to first or front-end part of ZK prover. On the other side, GPUs are natively focused on matrix multiplications through sensor cores, and they are they leave only, I think, even less than 5% of their resources for integer multiplications. On the other side, CryptoCPU entire instruction set and complete computation architecture is actually with special vector instructions and coprocessors is actually built to execute these special complex operations that we find in cryptography. And finally, which is very, very important, is that GPUs are usually composed of thousands of parallel units with limited memory assigned. And then, of course, you have a part of this limited memory that is assigned, you have problems of interconnections usually, because you have to move huge amount of data around. And then usually they use network on chip and stuff like that for shared high throughput memory. On the other side, we actually, through CryptoCPU, are not achieving these huge optimizations and latency cut by means of parallelizations, but by means of specialized computation methods. So, what are actual benefits of this? It means that we provide end-to-end acceleration with no migration cost. It's crucially important in this case. Then, for instance, results that we have obtained so far, I have to say that so far we have implemented most of this entire flow in FPGAs, and we achieved, for instance, we managed to cut latency of Solana validation by 50% and costs at almost 80%, because this kind of specialized hardware solutions, even in FPGAs, consume less than GPUs exactly because of their inefficiency when it comes to utilization of resources, available resources. On the other side, in the next generation, when we hopefully tape out the chip itself, the OpEx would be something like 100 times lower, and CapEx we expect to be 10 times lower compared to GPUs. Practically, finally, it enables easy programming and very, very flexible deployment in the sense that I mentioned. It can be plugged in any kind of server, can be also used standalone device, and so on. What does it mean in wider zero-knowledge proof context? Basically, essentially, it cuts latency, it cuts codes, and improves throughput, enabling, on the other side, huge number of real-time use cases, because the idea, now real-time is a little bit tricky. What's real-time? In Ethereum, real-time is practically 10 or 12 seconds, what is block finality, but many applications require it to be much lower than that, right? So that's why, among the other things, L2s exist. It boosts decentralization, which is very, very important, because for instance, all these kind of validators in this case could be completely decentralized, everybody could afford $200-300 to buy this kind of device and become practically full Ethereum node, because as I mentioned, we have RISC-V processor inside, and if eventually EVMs moves to RISC-V, we will be able to support not only consensus but also execution layer of Ethereum with this single device. Yeah, finally, of course, it improves censorship resistance, and crucially, I mean, it was here, but I think this importance of the fact that it's PQ enabled is actually growing. Why PQ and what does it mean PQ in our case is actually that we are collaborating with ZISC, and ZISC is supposed to be post-quantum resistant with, if I remember well, 128 bits of security. So let me just check how much time I have. Yeah, so this is there is essentially an initiative by Justin Drake himself to make a server for FPGA-based server for home proving project, a small kind of initiative between Ethereum Foundation, ZISC, and Ponos. And yeah, we are open for somebody else to join, of course. So the idea is that this is current situation that we have. So in order to make real-time proving, or 10 seconds, below 10 seconds proving of Ethereum block, we practically need at least 16 GPUs, which means a kind of huge, results in huge energy consumption. And it's, of course, huge, would be huge burden in terms of either CapEx or OpEx for any kind of provers that would like to run it. Our idea is to achieve below 10 seconds proof target, to have something like 4 to 5 times cost energy consumption reduction by this FPGA server compared to GPU server. And actually, the idea is to finalize this project by the end of the year. The idea is actually to replace entire this GPU farm with 4 to 8 FPGAs. And for us, this is a very nice demonstrator on the path towards ASIC. If we manage to prove that FPGA is able to provide exactly the same level of computation and speed as GPU farms with few times less, let's say, expense on energy consumption, it means that, for instance, if once put in ASIC, everything will go at least 10 times below. Because just frequency in which ASICs are operating are usually 10 times higher than those of FPGAs. Yeah, so this is a small recap. Basically, what we currently have, we have implementation in U55C board, but there is a next generation of V80, which has double resources, but much more importantly, it has next generation of PCI interface, which in practical terms means that this kind of bottleneck is removed. So currently, we are faster than RTX 3090, which is commonly used in improving servers at the moment. And yeah, so, and we have entire ZISC backend on FPGA already implemented. So practically, we need to finalize this complete end-to-end proving protocol. The most likely, to be very honest, this will be based on some combination of currently the Vitens generation should be done on a CPU host, while everything else will be done in FPGA. So that would be a kind of common configuration of the server. And yeah, finally, the idea is to surpass RTX 5090 on different kind of ZKP workloads, and yeah, to have single card sub 10 seconds Ethereum block proving. Oh, okay. Just a second. Oh, there was some gap. I think one slide is not shown, but anyway, we don't have much time. So yeah, the idea with this home proving server project is to showcase, to demonstrate possibilities of custom hardware approach in first phase with on GPUs, on FPGAs, and then later on by tape out in ASIC. So this is supposed to be a really ultimate solution for scaling ZKPs, and in practical terms, it can be analogically compared with Bitcoin miners. We may call it ZKP miner, and for whom it can be useful, practically for all infra providers, meaning large servers like, I don't know, Galaxy, for instance, can be used for different kind of on-prem deployment for enterprise use or whatever. And finally, it will enable standalone home users to have Ethereum proving directly in their homes for very affordable price. Because given this, I may tell you that currently to prove Ethereum block in real time, the consumption of GPU servers is around 10 kilowatts. With FPGAs, we hope to bring it down to 2 to 3 kilowatts, and in this case would be 200 to 300 watts, which is a kind of bulk consumption. So that's the roadmap that we hope to achieve with this chip. Thank you, and I would be happy to take any questions.
Thanks, nice talk. I'm just wondering about what different kinds of ZK systems you actually would support. So like hash-based versus elliptic curve, or different kinds of primes. Are there restrictions there, or?
Well, there are always restrictions, yes. But we are focused on hash-based commitment schemes like FRI, for instance. I may tell you some numbers. Our Poseidon implementation, as far I remember well in Goldilocks field, makes 83 million hashes per second. So we are mostly based on FRI commitment schemes. We have implemented completely Plonky 2 solutions. That is a core of ZISC, current existing ZISC, and also Plonky 3 solutions. When it comes to arithmetic fields, we are widely compatible with those mostly used. Marsen, Goldilocks, Baby Bear are fully supported for different set of instructions. That's one thing. Another thing, in general, all FRI-based, or if you wish, Stark-based provers are supported. And all those that are having actually RISC-V ISA generation as a base for witness generation. There are currently, I think, only one major ZK prover that is a kind of popular is excluded from this. Most of others are actually covered. Essentially, the point is that as long as those arithmetic operations are base for different kind of computation or whatever cryptographic primitive that is supposed to be computed, we are supporting that. That's why, for instance, we can support also signature verification, or which is a kind of in hashing. I think it's SHA-256 that are basis for Solana validation. So it's actually a portion of the chip, not full chip, but portion of chip that might be used there, still being much more efficient for this kind of purpose than anything else. That's the idea. Okay, thank you very much, and yeah.